In this video, we're going to continue talking about graphs of equations, but now we're going to focus on equations whose graphs would be a circle. We'll talk about the standard equation of a circle. We'll talk about how you come up with the equation of a circle given certain characteristics. We'll even talk a little bit about the equations of semicircles. As a starting point, let's look at the standard equation of a circle. The standard equation of a circle with center h comma k and radius r is the square of x minus h plus the square of y minus k equals r squared. Now you can just memorize this formula, but of course I'm going to show you where it comes from, because what kind of math instructor would I be if I didn't bore you with the details, right? So here's a circle, well let's pretend it's a circle, with center h comma k and radius r. That all of the points on the circle are the exact same distance away from some central point. Now that point could be anywhere. I chose some specific location. I'm going to call that point x comma y to represent that it's a variable point that could be anywhere on the circle. The distance formula tells me how I can relate these quantities together. I know that if I take the square root of the difference in the x coordinate squared plus the difference in the y coordinate squared, that should give me the distance between the points, and of course that distance is r. The difference in the x coordinates would be x minus h. The difference in the y coordinates would be y minus k. And if I square both sides to get rid of the radical, I get that equation of the circle, x minus h squared plus y minus k squared equals r squared. That equation is just a direct consequence of the definition of a circle and the distance formula. So if you have an equation in this form, you know its graph is a circle, and you can immediately pick off its center and radius. Let me go back to the one that I wrote a little bit nicer. You have to ask yourself what number is being subtracted from x to get the x coordinate of the center. Notice that it's x minus h. Similarly, you have to ask what number is being subtracted from y to get the y coordinate. The radius is not the number on the right. You find the principal square root of the number on the right in order to get the radius. So to get used to this equation, we're going to do problems of different types. We're going to start with a couple of problems where we come up with the equation given the properties of the circle. Then we'll do a couple of problems where we're given the equation and we have to come up with the center and the radius. Here's the most basic type. Find an equation of the circle which has center 4, negative 2 and radius 6. We know that the standard equation of a circle is the square of x minus h plus the square of y minus k equals r squared. We know the center and the radius here, so we can just fill in the blanks. We're going to square the difference of x and the x coordinate of the center, plus we're going to square the difference of y and the y coordinate of the center, and we set that equal to the square of the radius. X minus h, the x coordinate of the center is h, squared plus y minus k, the y coordinate of the center is k, squared equals the radius squared, r squared. And this can be simplified. This is x minus 4 squared plus y plus 2 squared equals 36. And there's the equation of the circle. Now this gives no context to why we would need the equation of the circle, but now we could find points on the circle by plugging in numbers for x, solving for y, or plugging in numbers for y and solving for x. We didn't actually need to find the equation of the circle in order to be able to graph it because we have all the geometric information we need. We know the center, we know the radius. We could have drawn the circle without the equation, but finding specific points on the circle could be difficult if you're graphing it by hand. We can use algebra now to find points on the circle if we wanted to. Let's find the equation of another circle, but in an instance where we aren't specifically told the center and the radius. This example says, find an equation of the circle with endpoints of a diameter at negative 2, 3 and at negative 6, negative 5. I'm going to draw the picture of this scenario on the next slide. We've got this circle with a diameter that runs from the point negative 2, 3 in the second quadrant to the point negative 6, negative 5 in the third quadrant. We need to find the equation of this circle. We just saw that if we knew the center and the radius, then it's easy to put this together. So I guess if we could find the center and radius in this diagram, then we'll be fine. You might recall we did an example like this earlier, where we knew the endpoints of a diameter and found the center and the radius. We find the center by using the midpoint formula, and then we can find the radius either by finding the distance between the two given points and dividing it by 2, or by finding the distance between the center and either of the two given points. Let's label the points. This is negative 2 comma 3. This is negative 6 comma negative 5. If I want to find the center, I use the midpoint formula. The x-coordinate of the midpoint is the average of the x-coordinate of those endpoints, so negative 2 plus negative 6 divided by 2. And the y-coordinate of the midpoint is the average of the y-coordinates of those endpoints, so 3 plus negative 5, also divided by 2. Negative 2 plus negative 6 is negative 8. Negative 8 divided by 2 is negative 4. Negative 3 plus negative 5 is negative 2. Negative 2 divided by 2 is negative 1. The center occurs at negative 4, negative 1. So the center of our circle is negative 4, negative 1. Seems reasonable based on my picture. My picture's not great, but the center would be around here. That's good. To find the length of the radius, we could either find the length of the diameter and divide by 2. I actually demonstrated that in a previous video. Or I could find the distance between the center and either of the two given points. So let's find the distance between the center and this point in the second quadrant, negative 2, 3. It doesn't matter which one I use. I'm just going to arbitrarily use the one on top. So I'm going to find the difference in the x-coordinates. That's negative 4 minus negative 2. I square that difference. I add that to the square of the difference in the y-coordinates, negative 1 minus 3 squared. And then I take the square root. That should give me the radius of the circle because I'm measuring from the center to the edge. Simplifying here, negative 4 minus negative 2 is negative 2, so this is negative 2 squared. Negative 1 minus 3 is negative 4, so this is negative 4 squared. Negative 2 squared is 4, negative 4 squared is 16. This is square root of 4 plus 16. Do not take the square root of each of those numbers. You have to add, and we get the square root of 20, which is not a rational number. You may have been trained to simplify expressions like this, and normally that's not a bad idea. Here I would encourage you not to. Let's just leave the radius as the square root of 20. The reason I'm going to leave it like that is, in the standard equation of a circle, we're going to square the radius. It's easy to square the square root of 20, so I'm not going to simplify that. Let's write out our formula. We do x minus the x-coordinate of the center, square that result, plus y minus the y-coordinate of the center, square that, set that equal to the radius squared. So simplifying, we get x plus 4 squared plus y plus 1 squared is equal to 20. And now we have the equation of the circle. We could check this answer by making sure that each of the two ordered pairs we were given satisfies this equation. So let's check really quickly. Negative 2 plus 4 would be 2. 2 squared is 4. 3 plus 1 is 4. 4 squared is 16. And 4 plus 16 is 20. This point works in the equation. What about the other one? Negative 6 plus 4 is negative 2, but negative 2 squared is 4. Negative 5 plus 1 is negative 4. Negative 4 squared is 16, and 4 plus 16 is also 20. Both of those points satisfy this equation, and so it's got to be the right one. This is the equation of the circle with diameter at negative 2, 3, and negative 6, negative 5. Okay, so we've done two problems where we were given characteristics about a circle, and we found its equation. Let's go the other way. Let's take the equation of a circle and find some characteristics of it. Here's a simple example. Find the center and radius of the circle with equation x squared plus the square of y plus 2 equals 40. So here we have the equation and we want to find the center and the radius. Well, we know we can pick off the center and the radius if it's written in this standard form, and we almost have that exactly. The one thing that looks different is that we don't have a binomial squared with the x. We just have x squared. But if you think of that as x minus 0 quantity squared, leaving the other terms exactly the same, now we have it written in the standard form. So to find the center, we ask ourselves, what is being subtracted from the two variables? Well, we're subtracting 0 from x, so the x-coordinate of the center is 0. Here you don't see subtraction at all, but if you think of that as y minus negative 2 inside the parentheses, then you can pick off the y-coordinate of the center, which is negative 2. So the center is 0, negative 2. The radius is not 40. Remember that the radius is being squared here, so we take the square root of 40, which happens to simplify. You could rewrite this as the square root of 4 times the square root of 10, which is 2 root 10. I think the square root of 40 is a fine answer here. So if we have the equation in standard form, it's easy to pick off the center and the radius. But not every equation of a circle comes in standard form. Here's an example of that. Find the center and radius of the circle with equation x squared plus y squared minus 10x plus 14y equals 7. Looking at this, we don't immediately know that this is a circle, and we can't pick off the center and the radius. So what we're going to do is we're going to rewrite this in the standard form. And the process we use to do that is called completing the square. Let me give you a quick reminder of how completing the square works. Completing the square takes advantage of a pattern in perfect square trinomials. So as a reminder, a perfect square trinomial is the result of using the FOIL process on the square of a binomial. I've written this so that we're factoring it from left to right, but it might actually make more sense if we work from right to left. If you square x plus m, that means you're taking x plus m times x plus m. And x times x is x squared, and the outer and inner terms are both mx, so you get 2mx, and then m times m is m squared. If you have minus signs instead of plus signs, then your middle term is negative instead of being positive. Now what are we going to do with this? Well, what I want you to notice is if we take half of the coefficient of x, whether it's 2m or minus 2m, if we take half of that, we get m. And if we square that, we get m squared. So in a perfect square trinomial, the constant term, the numerical term, is always the square of half of the coefficient of x. So if we have an expression where we have an x squared term and a linear term, and we want to complete the square, turn that into a perfect square trinomial, we take half of the coefficient of x, so half of b would be b over 2, and we square that result. And then if we're using this to alter an equation, then we have to compensate somehow. So instead of talking about this abstractly, let's go back to our example and talk about how we're going to do this. First, I'm going to reorder the equation so that the x terms are together, and I'm going to leave myself a little bit of space to complete the square. And then I'm going to put the y terms together, and I'm going to leave a little space to complete the square there, and we're going to set that equal to the 7 on the right side. The pattern that we have in a perfect square trinomial is that the constant term is the square of half of the coefficient of the linear term. So we take half of the coefficient of the linear term and square it. That guarantees that we'll have a perfect square trinomial. So with the x's, to complete the square, I take half of negative 10 and square it. So negative 10 divided by 2 squared is negative 5 squared. That's 25. So I'm going to add 25 to complete the square. The constant term is always added on the end. You're all good enough at factoring to know that this is going to factor to x minus 5 times x minus 5. That is, it factors to a perfect square. This is x minus 5 squared. And now it's in a format where we can easily pick off the center. The x-coordinate of the center is going to be 5. However, I just altered the left side of the equation. I added 25 to it. I have to balance that somehow, and the obvious way to do that is to add 25 to the right side as well. Whatever you do to the left side, you do to the right side. We're going to do the same thing to the y's. See if you can come up with the number that will complete the square there. Okay, going back to the rules, we take half of the coefficient on the linear term and square it. Now we're working with y's instead of x's, but don't let that bother you. The rule is the same. We're taking half of the coefficient on the linear term and squaring it. So here the linear term has a coefficient of negative 14. I take half of that and square that result. So half of negative 14 is negative 7. Negative 7 squared is 49. And I add 49 to the left side. That guarantees that this will factor to the square of some binomial. See if you can figure out what it is. Again, y'all are good enough at factoring that you can probably do this without using any tricks, but let me show you something that's kind of handy. If you look back at our pattern, the number in the parentheses is just the number that you squared. So in our work, we squared negative 7. So this is going to be y minus 7 quantity squared. Check it out, you'll see that it works. Because we added 49 to the left side, we have to compensate by adding 49 to the right side. Now we just do the arithmetic on the right side. 7 plus 25 is 32. 32 plus 49 is 81. Now that we've written it in standard form, see if you can pick off the center and the radius. The center is 5, 7. We're subtracting 5 in the first term, we're subtracting 7 in the second term. The radius is not 81, the radius is the principal square root of 81, which is 9. I'm going to show you how to find the equations for the upper half, lower half, right half, and left half of the circle with the equation x squared plus y squared equals r squared. Geometrically, this is a circle with center 0, 0, and radius r. So this is a circle centered about the origin. So this circle is going into all 4 quadrants. So how do you go from the equation of a circle to the equation of a semicircle? When the semicircle is either the upper half or the lower half, like in these examples, you've really restricted the value of y in a particular way. In this example, when you're looking at the upper half, all of the y coordinates are positive, and when you're looking at the lower half, all of the y coordinates are negative. So the idea is we're going to solve for y in the equation of the circle, and then make sure that those y values either come out positive or negative depending on which half of the circle we want. The equation of our circle was x squared plus y squared equals r squared. We're going to solve this for y. So first we would subtract x squared from both sides, and we get y squared equals r squared minus x squared. And now to turn this into a y, we take the square root. And normally we have to do plus or minus, but we know we don't want plus or minus here. We only want the positive results, and this is how we go from the equation of the circle to the equation of the semicircle. If I stop with y equals the square root of r squared minus x squared, considering only the positive roots, then my y coordinate is always non-negative and I only get the upper half of the circle. How do I get the lower half? Well, I start with the same circle. I do the exact same step. I get y squared alone. And now I try extraction of roots again, but to guarantee that I get the lower half of the circle, I only consider the negative roots. And now I won't get any positive y coordinates and I only get the lower half. We can do the same thing for right halves and left halves. We just have to recognize that now we're talking about x coordinates instead of y coordinates. In the right half of that circle, all of the x coordinates are non-negative. In the left half of the circle, all of the x coordinates are non-positive. So I'm going to solve for x in each of these and then just choose the root that gives me the correct side. So I start with x squared plus y squared equals r squared. And in fact, I said I was going to do it, but why don't you do it? Solve that for x and then choose the correct sign in order to get either the right half or the left half. If I want the right half, I'm going to subtract y squared, get that x squared equals r squared minus y squared, and then when I use the extraction of root step, I just focus on the positive roots to get the right side. If I want the left side, I still solve for x. I'm going to subtract y squared from both sides. X squared equals r squared minus y squared. But when I do the extraction of root step, I only consider the negation of the principal roots. That's what's going to give me negative x coordinates and give me the left half. Now you can generalize this to circles that aren't centered about the origin. When you want the right half of the circle, you solve for x and consider the principal roots, and when you want the left half of the circle, you solve for x and you only consider the negation of the principal roots. The idea is the same, but it can be a little more complicated than this. I just wanted to give you an overview of semicircles. So we covered the standard equation of a circle. We talked about how to get the center and radius from that equation. We talked about how to come up with the equation given information about the circle. And we talked about the equations of semicircles. If you have any questions for me, need anything clarified, please find me in an office hour or shoot me an email.